we have different algorithms available to us, which we have, and we come across new algorithms every once in a while. So we will be trying to guess the waiting times for these algorithms, right? So the first algorithm for CPU scheduler is called first comes first served. Naturally, the easiest thing to do is that you have a ready queue, and you simply keep on uh, counting, or keep on recording the arrival times of all the processes. So what do? You uh, record the arriving order of the processes. For example, in this picture you can say that P1 was the first one to arrive, P2 was the second one to arrive, and P3 was the third one to arrive in the ready queue. Ready queue was empty before, and then P1 arrived, after that P2 arrived, and after that P3 arrived. So this is the arrival order of all the processes, right? So though, even though it may not sound like a proper algorithm, this is something that we have decided to do, right? That's why we can call it an algorithm, because this is a decision that is taken by us, that we are going to note down the order of arrival of all the processes, and we are going to dispatch them in the same order. The oldest one is going to be sent first. That means the first come will be first served. So this is a decision taken by us. That's why we call FCFS is a scheduling algorithm, right? So the first one to arrive in this is P1. So we send P1 to the CPU, and P1 had to stay in the CPU for 24 seconds, right? But the thing is, I just want you to keep in mind at this point that it may not be easy for the operating system to guess these times, because the code of an operating system is something that you never go into. The operating system never goes into the code and see operating system doesn't have time to go into the code of a program to see how much time that program is going to stay in the CPU. Just like, if I look at this code, and I'm certain that this is the amount of time, because this is an IO instruction and this is another IO instruction. So this is the amount of time this particular program is going to stay into the CPU. The operating system never does that. The operating system never has the time to do that, right? Because it has so many other things to do. Okay, these were the expected running times for, like, P1 was expected to run for 24, P2 was 3, and P3 was expected to run in the CPU for 3 seconds. The arrival order was just like this: P1, then P2, then P3. And because this is the first come first served scheduling algorithm, we will be selecting the first process that arrived. So we will be sending P1 to CPU, and P1 was sent at time 0. It stayed in the CPU for 24 seconds, and then P2, and then P3. P2 stayed in the CPU for 3 seconds, so 24 plus 3 is 27. And then P3 was sent, and P3 stayed in the CPU for 3 seconds, so 27 plus 3 is 30. So this is our timeline. This is called a Gantt chart, and the Gantt chart gives us a clear view of what is going on with the processes and how they are selected and how they're scheduled. And it's very easy, if you have drawn it properly, it's very easy to see the waiting time for all of these. All of this picture was available to us at t equal to 0. So that means all the processes should have been gone into the CPU at t equal to 0, but only one of them was sent to the CPU at t equal to 0. So the waiting time for P1 would be 0. Because P1 was available at 0, it arrived at 0. We somehow know the amount of time a process will be staying in the CPU, right? So we will see how. So the first come first served scheduling algorithm says that simply select the oldest process and send it to CPU. So at t equal to 0, we sent it to CPU, and it took 24 seconds to finish. And then we selected the second process, and it took 3 seconds, went up to 27, then P3 was sent, it took 3 seconds, we landed on 30. So this is the complete timeline for these three processes. In order to calculate the waiting time, we saw that P1 was not put on wait. P1 did not have to wait at all. P2 on the other hand had, because it was available at t equal to 0, but P2 had to wait 24 time units. So the delay for P2 would be 24. Similarly, the delay or the waiting time for P3 would be 27. In order to calculate the average waiting time, you simply add these three things together and divide by 3. Okay, so right, so the average waiting time for this case, you can say, or this scenario, is 17 time units. So some of you may be thinking, must be thinking actually, that if we scheduled these processes first before this one, the average waiting time would be less, right? So let's look at a slightly varying example. That, for example, this arrived first, this arrived second, and this one arrived third, right? What would happen if that was the case? So this is the arrival order. If this was the arrival order, P2 will not have to wait at all. So P2 waited 0. P3 had to wait 3 time units. So the waiting time for P3 is 3. And P1 had to wait only for 6. So this is the waiting time for P1. The average waiting time now is 3. So the average waiting time went down from 17 down to 13, right? So this is a drastic change in average waiting time, and obviously this is a good thing. This one is very good, and this one is not so good, right? So we want the system to do something like this instead of something like this. But the thing is, this is not in our control if we are using the first come first served scheduling algorithm. If we are using this algorithm, this is not in our control to change the order, because the order is dependent on the arrival time, and this is not in our control as far as we are using this algorithm. By the way, this is also a non-preemptive algorithm. If one process takes over the timeline, we are not allowed to cut out its execution and take it out of the CPU forcefully. We cannot do that. Once a process goes into CPU, unless it leaves the CPU on its own, we cannot bother that process, and we cannot force it to come out of the CPU. This is a non-preemptive algorithm, and this particular, you can say, a defect with the algorithm, that the arrival time, sorry, the average waiting time is so high, is called convoy effect. Convoy effect is when the timeline is taken over by a process which has a very large amount of CPU burst, and it prevents a small CPU burst process or multiple processes with small CPU bursts from quickly running into the CPU, because they could quickly run in the CPU just like this, and they would make the timeline free, make the CPU free. But in this scenario, P1 prevented that from happening, and it took over the timeline, and the CPU was taken hostage by this process which had to run for a very long time. So we say this is convoy effect. And why the name convoy effect? Because if this was a large truck with very slow speed, and these two were sports cars with very high speed and lightweight, now, and it was a single lane road, you can say that the truck has taken over the road, and until this truck goes off the road, these sports cars cannot go any faster. So they are just so all these three vehicles are just like a convoy, uh, in which this truck is leading the convoy,